When I'm at the supermarket on a weekly basis, I often pick up a bag of Mars variety mix. Not because I have a chocolate addiction or because I use it to bribe students into doing some work, but because it can be used to teach chemistry. In fact, the rest of the video, we can actually learn all of the concepts we're about to do using this one bag of Mars variety mix. If you open the bag up, what you end up with is a collection of different chocolates, 6 Mars bars, 5 Milky Ways, 5 Snickers, and 4 M&M bags. And you can use these numbers to work out how many of each chocolate you can get if you get a few more bags. To do this, you can turn these numbers into a ratio. For every one overall bag you have 6 Mars bars, 5 Milky Ways, 5 Snickers, and 4 bags of M&M. So a question I might ask is, if I have 13 of these share packs, how many Mars packs do I have? To do this, we can go back to our ratio and use the numbers given there. Now you may just be able to do this intuitively, but I'm going to show you a step-by-step to apply that ratio, and this will be useful in future questions. So what we do is we have the number of share packs, we divide that by the share pack number in the ratio, and then we times by where we're going. So divide by where we start, times by where we're going. Yeah, so we go 13, divide by 1, times by 6. I can just times by 6 in this case, but the divide by 1 becomes important later on. So 13 times 6, and that should give you 78. If I change this around a little bit and ask you the reverse of this question, I have now 12 Mars bars, and I want to work out how many share packs this came from. So we know that 6 Mars bars is 1 share pack, so 12 straight away would be 2, twice as many. But there is a systematic way to work this out as well. Again, you use your ratio. You go 12 divided by 6, divide by where you start, times by 1, times by where you're going. So 12 divided by 6 times by 1, and that should give you 2 share packs. Ratios become particularly handy when you're working with slightly more challenging numbers. So if you end up with something like this, I have 30 Mars bars, but now I want to use that number to work out how many M&M packs I have. So I don't want overall bags, I now want to know M&Ms. Now this becomes a little bit more challenging. You might be able to do it intuitively, but we need to apply our ratio. And the way we're going to do it is exactly the same as we've done the other ones. We're going to take that 30, we're going to divide it by the ratio number where it starts and multiply by where it's going. So divide by 6 times by 4. And that gives us 20 M&M packs. The point here is we've got a ratio, and that ratio, regardless of how you look at it, can be used to work out amount of one thing having been given amount of another thing. These ratios are really important. The way you apply them might be different. I've just shown you this way of applying it. You might have your own ways, that's fine, but the point is we need to be able to apply these ratios. We can apply this exact same concept to chemistry. If we took a chemical formula, any chemical formula, like the one shown here, C2H5O2, we can split it up and look at how many of each component we've got. So one C2H5O2 contains 2 carbons, 5 hydrogens, and 2 oxygens. We can also write that as a ratio. So every one C2H5O2 is to 2 carbons, 5 hydrogens, and 2 oxygens. We can use this ratio in the same way that we used the last one. You can take this a little bit further and also say that if every one molecule of C2H5O2 gives you 2 atoms of carbon, we can apply this exact same ratio to moles. So 1 mole of C2H5O2 will give you 2 moles of carbon, 5 moles of hydrogen, and 2 moles of oxygen. Because this ratio is a ratio of amount, and both counting individual atoms as well as dealing in moles both relate to amount, quantity, you can use the same ratio. What we're going to do is a couple of problems now involving this ratio. So if I had a question like this, I have 3 moles of the whole thing, C2H5O2. How many moles of carbon atoms are there? I want to know how many collections of carbon atoms I have. What I do here is once again apply the ratio. I go 3 divided by 1 times by 2. So 3 divided by 1 times by 2, that should give me 6 moles of carbon atoms. So separate question, if I have 10 moles of oxygen atoms, how many moles of C2H5O2 can I make? Again, you use the ratio, so you go 10, and in this case, because we are using oxygen, we go 10 divided by 2 from there, times by 1 from there. And that should give us an answer of 5 moles. So if I have 10 oxygens, 10 moles of oxygen atoms, I can make half as much of the overall thing because their ratio is 1 to 2. Now there are other ways to apply these ratios, by the way. You might have a better way to apply it. Some people, for example, do it intuitively. They know that you have half as much of the overall as you do oxygen. So for every oxygen you have half as much as the overall, so you can half the number. That works too. Some people also prefer to just apply it in one hit, so they do 10 times a ratio of, in this case, 1 over 2. That's fine too. That works. However you apply ratios is fine, but I'm just giving you a way to do it. Things get slightly harder if you start looking at the ratio of oxygen to hydrogen. So let's say I've got 16 moles of oxygen and I want to know how many hydrogens I have. What I do here, though, step by step, is exactly the same. I do 16 divided by whatever oxygen's number is in the ratio. In this case, it is 2, divided by 2, and then times by hydrogens, which is 5. So I go 16 divided by 2 times by 5. And that should give me an answer of 40. 40 moles hydrogen. Now that seems like a lot, but look at the numbers there. Every 2 oxygens gives you 5 hydrogens, a lot more hydrogen. So 16 oxygens giving you 40 hydrogens kind of makes sense. Always look at your numbers to see if they actually add up and make sense. So in this way, you can use ratios to work between substances, to work out amount of one thing having been given the amount of the other. If someone asked a slightly different question, let's say someone said you have 50 grams of Snickers bars. We don't know how many Snickers bars that is. That might be 1, might be 2, but we know that's 50 grams. And we wanted to work out how many Mars bars we had. We couldn't just apply the ratio from our share pack earlier into this mass because Snickers bars and Mars bars way different. That ratio was based on quantity, not on mass. So what we've got to do is take that 50 grams and convert it to quantity. We've got to know how much one Snickers bar weighs. It's much the same when you're dealing with moles. So if I had a question like this, if I have 122.12 grams of the whole thing, how many moles of oxygen does this contain? What I've got to do is work my way into moles. I can't apply this ratio to grams. So what I've got to do is use my molar mass calculation. Remember, number of moles equals mass over molar mass. I'd have to go off and work out the molar mass of this substance. In this case, I'll save you the trouble. The molar mass is 61.06. And then the mass in this case is 122.12. When I solve for that, that gives me 2. N equals 2. Now remember, this is the moles of this substance, right? I've got the moles of the overall substance. That's what I've just worked out using molar mass. I've now got to work out moles of oxygen. So, and the way you can represent this is by writing little subscripts. So I can say number of moles of oxygen equals 2, and then you apply the ratio divided by 1 times by 2. So 2 divided by 1 times by 2. And that should give you 4. 4 moles of oxygen in that many grams. So when you're working with grams, liters, mils, pressure, whatever it might be, you've got to first work your way into moles and then apply molar ratios. Now finally, what if you had a question similar to this, where it said if you had 0.5 moles of the compound, how many atoms of oxygen do you have? So if you have a question like this, it's asking you not to find moles of oxygen, but actual atoms of oxygen, how many individual atoms of oxygen you have. Our analogy kind of breaks apart over here, but we can kind of think of it in terms of the M&M's pack. So every family pack has individual packs of M&Ms, but then the individual packs of M&Ms also have individual M&Ms. In the same way, a mole of the compound will have certain moles of oxygen, But then if you look a bit deeper, that mole or two of oxygen will have individual oxygen atoms. So you've got to go a layer further. And that's what this question's asking you to do. So the way we do this question is we start off in the same way as the previous ones. We apply our molar ratio. Why? Because we're going from moles of one thing to moles of another thing. So our molar ratio will get us to do 0.5 divided by 1 times by 2. So we're going to go 0.5 divided by 1 times by 2. That'll give you 1 mole oxygen. The next thing you've got to do though is turn the moles of oxygen into actual number of atoms. And to do this, we've got to bring back one of our formulas and one of our numbers, our Avogadro's number. So we've got to go number of atoms equals number of moles times 6.02 times 10 to the 23. Now because number of moles is 1, this just becomes 1 times 6.02 times 10 to the 23, which works out to be, 6.02 times 10 to the 23. And that's your answer. So to do more practice like this, or any of these questions, please go to page 51 of your activity books. Do as many of those questions as you can. And once you're done, check your answers and move on with your lives. Thanks for listening.